Swati Verma, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, CSVTU Bhilai. I welcome you all to the course on Industrial Automation and Drive. Today, we will start with our 12th lecture with the title PLC Programming. Till now, in the 11th lecture, we have seen the software related to the PLCs, the memory organization in a PLC software, and also the PLC programming addressing. And end of the 11th lecture, we have also completed the scan time of the PLC. In today's lecture, we will start with the PLC programming with the basics of binary concept. Now the binary concept. The programmable logic controller, like all the digital equipment, operates on the binary principle. The term binary basically refers to the idea that many things can be thought of as existing in only one of two states. For example, these states can be 0 or 1. Means the 1 and 0 can be represented as a on or off, open or close, true or false, high or low, or any other two conditions like the absence or presence of anything. Okay, so the binary means two states. Okay, clear. Now the next is the key to the speed and the accuracy with which this the binary information can be processed is that there are only two states, each of which is distinctly different from each other. Means one is opposite or distinctly different from the 0. Open or close, like true or false, these all states are indistinctly different from each other. Next, the logic gate. The logic gate is a circuit which performs a binary operations. It is a circuit with several inputs but having only one input, which is activated by particular or certain combination of the input conditions. Logic is generally defined as the ability to make the decisions when there are two or more different factors must be taken into account before any action is taken. Like take an example basic for the operation of the PLC, where it is required for a device to operate only when certain conditions have been met or certain conditions or factors have satisfied. Generally, there are three broad types of logic gates which are available. First is the basic gate, which includes the AND gate, OR gate, NOT gate. Second is the universal gate, which is the NAND or NOR, and then the special gates, which are XOR and the XNOR. Next, we will discuss in detail about the AND function or the AND gate. It is a device with having two or more inputs but having a single one output. What is the AND function? The AND gate will output high or 1 only if all these conditions are satisfied or only if all the inputs are 1 or high. In the figure, you can clearly see the logical symbol of the AND gate having two inputs A and B and the output designated by the Y. Here you can clearly see the truth table of the AND gate which has three columns of two inputs A, B and Y as the output. Here you can see the output Y is only high when both the inputs A and B is 1. And if any of the input A and B is 0, the output is also 0. Means to make the output high of the AND gate, both conditions or both the inputs or all the inputs should be high or 1. Here you can see the AND gate cases. The first case in which input is 0, 0 is given, the output is 0 or low. Second case, input 0, 1, output is 0. Third case, input is 1, 0, output is 0. And in the last case where the input A and B is 1, 1, output is high or 1. Here you can also see the circuit in the AND gate in the circuit form represented by a input battery, output light indicator, and logic gate by switches, switch A and switch B. Generally, the AND gate is represented by the series combination of switches A and B. Here you can see the truth table. When both the switches are open, the output is off since the circuit is not complete, and if both the switches are closed, means 1, 1, the output is on or the output is high. Here you can also see the logical representation of the AND gate in the form of switches and the light indicator. Next is the OR gate. The OR gate can have any number of inputs but only one output like the AND gate. Similarly, the OR gate will output 1 if any of its input or if any of the condition is met or any of this input is high or 1. Like you see in the figure, the logical representation or the logic symbol of the OR gate with inputs A and B and the output Y. Here you can clearly see all the 4 cases. Since I can clarify here that here there are 2 inputs, we are using the 2 inputs A and B, so only the 4 cases are possible. Means I input can be 0 or can be 1. So we have the 4 cases, similarly 0 0, 0 1, 1 0 and 1 1. For all this input combinations we have shown the output in the truth table. Here in the truth table you can see when the input A and B is 0, the output is 0, and if any of the input either A or B is 1 or high, the output is 1. Here you can see the the representative circuit in the form of switches with the battery similarly or the light indicator. Here to make the OR function, the switches are connected in parallel form or in a parallel connection. You can see the truth table here. If both the switches are open, okay, the light is off, means there is output is 0. But if any of the switch is closed, either A switch is closed or B is closed or both the switches are closed condition, output is on or the light will glow or the light is on. You can clearly see all the 4 cases in the logical diagram here. Okay, 0 0, 0 1, 1 0 and the 1 1 case. Here in the OR function we will get only the 0 output only in one case when both the inputs are 0. We will get the high output or 1 output in all the rest 3 cases in 0 1, 1 0 and 1 1 case. Okay. This is a NOT function. The NOT function can have only one input. Okay. And similarly it is inverse of the input, the output is inverse of the input applied, which means the NOT output is 1 if the input is 0 and the output will be 0 if the input is 1. Okay, so means the result of the NOT gate is always the inverse or complement of the input provided. So by this function of the NOT gate, it is commonly called as inverter gate also. Here you can see the logical symbol of a NOT gate provided with a single input and a output light. Here you can also see the truth table and the hardware circuit representation of the NOT gate. Here we have simply applied the NC push button with the light and the output, and you can see in the table that if it is push button is not pressed or 0, the light is on, and if it is pressed means it is activated or it will change its state to the normally open and the output will be off or the light will be off. Next, the NOT function is the most used in the conjunction with the AND or the OR gate to design the NAND and the NOR gate. Okay, the NOT symbol placed at the output of AND gate would invert the normal output result of the AND gate and will represent the NAND operation. Simply the AND gate with an inverted output is called as a NAND gate. Here you can, in the figure you can clearly see the NAND gate symbol and its truth table. Here you can see that if in you can revise the things that in the AND gate, if any of the input is 0, the output will be 0, and if both the inputs are 1, then only the output is 1. So just the inverse case here, if both the inputs A and B are high, the output is 0, while if any of the input is 1, output is 1, and if both inputs are 0 or low, then also the output is 1. You can simply remember the truth table of the AND gate and simply invert it to get the truth table of NAND gate. Similarly, it's the same case applies with the NOR gate. If the NOT symbol is placed at the output of the OR gate, it will become a NOR gate. Means if the normal output of an OR gate is inverted, that function will be referred as a NOR gate. Okay, here you can clearly see the symbol of the NOR gate and the truth table associated with it. In the OR table, if you have remember, in the OR gate, if any of the input is high, the output will be high. Okay, and if both the inputs are 0, output will be 0. But here in the NOR table, both the inputs are 0, then only the output will be high. If any of the input is 1, the output is 0. Okay, clear? It's just inverse operation of the OR gate. So the NAND function is generally used in the integrated circuit, or the NOR function and the NAND function is basically used in the integrated circuit logic arrays and can be used in the programmable logic controllers to solve the complex logic. And as I have said earlier, that this NAND and the NOR gates are called as universal gates, because by using this NAND and NOR gate you are able to design all type of gates. Means by using this NAND and NOR gate you are able to design the AND gate, OR gate, NOT gate and the special gates also. Next is the special gate, the exclusive OR, also called as the XOR gate. Here you can clearly see the symbol, the logical symbol of the XOR gate and the truth table associated with it. Here you can clearly see in the truth table, the output is high and the output is 1 when any of the input is high, or if any of input is different or opposite of the second input. Means if the both inputs are different in nature, means one input is 0, means A is 0 and B is 1, then only the output will be high. If both the inputs are in same condition, then the output is 0, which means if A is 0, B is 0, output will be 0. If A is 1, B is 1, output will be 0. Since here the input A and B are same, either 0 or both are 1, so output will be 0. And if both inputs are different, for example A is 0, B is 1, A is 1, B is 0, then the output is high or the 1. Okay, next is the exclusive NOR gate or XNOR. The XNOR is a logic gate where the output will be high if both the inputs are same or the equal. It is just inverse of the exclusive OR gate where the output is high, where the inputs are different. Okay, in the exclusive NOR gate, if the inputs are same, then only the output will be high or 1, and if the inputs are different, okay, if they are different, then the output will be 0. Here you can clearly see the logical symbol of the XNOR gate and the truth table. Here with the first case, if the A is 0, B is 0, output is 1, since the A and B are same. Similarly, if A is 1, B is 1, the output is 1. Next, if the A is 0, B is 1, and if A is 1, B is 0, output is 0. So it will only give the high output if both input are same, and it will give the low output or the 0 output when both the inputs are different or not same. Clear? Just exclusive NOR is the inverse of the exclusive OR gate function. Now next is the ladder programming. As I have mentioned in the earlier lecture, that there are different types of PLC programming. Okay, but since the most commonly used and the user friendly is the ladder programming, so in our lecture we will use the ladder programming to program our PLC. Clear? Here you can clearly see in the figure there are the two rails. First is the left rail and next is the right power rail. The power flow, generally the power flow between these two rails, okay, and the direction is, the power direction is always from the left power rail to the right power rail. Now the joining line between these two rails, this left, the line joining between the left power rail to the right power rail is called as the rung. There can be many rung in a diagram, in the ladder diagram. Each ladder diagram is ended by a AND rung, which is not, there is no need to program the AND rung. Okay, it just signifies the end of the ladder diagram. Okay, so there can be many rungs, like you can see in the figure that there are rung 1, rung 2, rung 3 and rung 4. In the black solid line, you can clearly see the direction of the power flow. Generally, the direction of the power flow is from the left power rail to the right power rail, and it flows sequentially manner and downward in the rung. For means, first the power flow will be from left power rail to right power rail in the rung 1, then the power will be switched to the rung 2 from the left power rail to the right power rail, then power will be switched to the rung 3, then will be to the rung 4. Means it will flow in that exact manner like you see in the diagram. Okay, and now in the ladder programming, generally we have two input types and the one output type. Here you can clearly see the symbol for the two input, which is generally normally open and the normally closed switch. Okay, and the output symbol you can see as a spherical close half. Okay, the input symbols are generally normally open and the normally closed, and there is only one output symbol which is you can see in the diagram. Next third figure is the RX Logic X 500 software view, in which we are going to design, or in which we are going to design our ladder, or in which we are going to program our PLC operation. Okay. Now next, before starting with the programming, you must knew about the some ladder programming rules, which are very important to design any programming or do any PLC programming. Okay, first rule is that the rung is not blank at the left power rail side. Okay, means in each rung one input is compulsory. Okay, the input can be normally open or input can be normally closed type input type. Okay, here you means in clear, every rung should have a input. It can be normally open, it can be normally closed, but there must be a one input in each rung. There can be many inputs in a rung, but at least there should be one. Okay, you can clearly see in the diagram, in the first ladder diagram picture, there is no input attached to the rung, so it is a wrong way. In the next diagram you can see we have attached a input. Okay, means you can see the normally open and a normally closed switch here, so it is a right way to provide an input. Okay, how to design a ladder. Next is, the rung is not blank at the right power rail side. Means in each rung one output is compulsory. Okay, here you can clearly see, like I have first rule, the input is necessary in each rung. Similarly, there can be one output, or there must be a output in each rung. Okay, in the first diagram you can see, which is a wrong way to design the ladder, the two inputs are connected but there is no output connected to the left rung. Similarly, but in the second figure you can see, which is a right way to connect input and output, here the output is also connected to the right power rail, so it is a correct way to attach or connect any input or the output in a ladder diagram. Okay, so in any rung in the ladder diagram, there must be a input or there must be a output. Next, here the third rule, the output cannot be connected in series, only the parallel connection is valid. Okay, means if you are connecting two or more outputs in a rung, it must be connected in a parallel connection. It can't be connected in a series. So as you see in the first diagram, here the two outputs are connected in series form, which is not valid in a ladder programming. In the second diagram you can clearly see, here the outputs are connected in the parallel form, which is a correct or the valid form of connecting a outputs. Fourth rule, the input is connected to the input side and output is connected to the output side. Okay, here you can see means the output should be connected to the right power rail or the right side of the rail, and our input should be connected to the left side of rail. Okay, in the first diagram figure you can see the output is connected to the left rail, then the inputs are connected, which is a wrong way of connecting the input and output. In the second figure you can see first the inputs are connected, then the output is connected, which is a correct or the valid way to connect the input and output. Because like I have shown earlier, the power flows from the left rail to the right rail. So, or generally in the electrical circuit, you also know that current will flow from input to the output side to energize the output. So here the input should be connected to the left rail side, then the output should be connected to the right rail side. Okay. The fifth rule, we can provide the same input address to two input switches, but they cannot be connected in series. Means in clear way you can see we can connect two or more switches in the series connection in a rung, but we can't address them in the same, we can provide the same address to both the inputs. Like you can see in the first figure, we have connected two normally open switches in a rung with the input address I0 colon 1, I0 colon 1. We have provided same address to both the inputs and they are connected in series, which is not a valid or it is a wrong way. Okay, and in the second figure you can see we have connected the two input switches in series, but we have given them the different addressing. Means first switch we have given the address to I0 colon 1 and second input we have given the address I0 colon 2. Okay, means we can connect two inputs in series, it's valid, but you can't provide same addressing to the inputs connected in series. Okay. Okay, next, now the sixth rule, the input address cannot be used as an output address, but the output address can be used to address any input switch. Okay, means you can clearly see in the figure in the first rung there are two input switches with the address I0 colon 1, I0 colon 2, and there is an output connected to the first rung with the same address like the input, means I0 colon 1, which is a wrong way. You can't address any output switch like the input. Okay, but you can address any output switch like an input, which means like you see in the next or the second diagram which is written right way. Here the two inputs are connected with the I0 colon 1 and I0 colon 2 address, and the output with the address O0 colon 0. And in the next in the second run you can see a normally open switch with the same address like the output of the first rung with the address O0 colon 0. Okay, this is the right way. You can address any input switch with the same address like the output, but you can't address output in terms of the input address. Okay, because generally it's like in electric circuit you have used, we can use the output of any device or output device to drive and like an input for any other system. Similarly in the ladder diagram also you can use any output to drive the input. So you can, any input device can take the address of the output. Okay, now the seventh rule, the same input address and the same output address can be used as many times in the program, but you have to remember all the same address will respond simultaneously, which means if there are two or three switches having the same address and if you give one to any of the switch, all the rest of the switch will change its state. Okay, generally I like to clear this that if it is a normal open switch and you give high input or the 1, okay, then giving any input to a switch means it will toggle its state or it will change its state. Okay, and if you give 0 to any switch, it will not change its state and it will remain to its state, which means if you give 1 to any input switch, it will change its state. Means if it is in open case, it will switch to the closed, and if it is closed, it will change to the open condition. But if you will give 0 to any input, it will remain in that state only. If it is closed, it will remain closed. If it open, it will remain open. Clear? So if you want to change the state of any switch, input switch, you have to give him 1 or the high input. Like you see in the diagram, in the first rung we have I01, first switch I0 colon 2, the second switch, okay, and in the second rung we have connected input switch with the same address like the rung 1 I0 colon 2. So like you can see, it is energized. If it is a green line, means it is active or you have given the high input to it. So if you have given the high input to any of the switch, all the other switches in the other rungs having the same address will also respond or will also get one or will get activated. Clear? Or will change its state, you can say in the clear words. Okay, so now let's make a lid. That's all about the rules which you have to keep in mind while doing the ladder programming. Okay, so now we will do the ladder program for all the types of the logic gate which we have discussed. Okay, now first start with the AND function. Like I have already explained, the AND gate can have 2 or more inputs but only a 1 input. But the commonly used is 2 input AND gate. So here also we will consider the 2 input cases A and B and a single output Y. Okay, the AND gate, as we remember, will only give the high state or the high output if all the conditions or all the inputs are high. Means for the 0 0, 0 1, 1 0 cases, means case 1, case 2, case 3, it will give the 0. And if in the case 4, when both the inputs are high, 1 1, then it will be high. Okay, as you see in the ladder diagram, the AND function is represented by a series connection of 2 switches. In the figure you can see all the 4 cases of the AND gate. Okay, the case 1, when A is 0, B is 0, the output will be 0. So here you can clearly see in the ladder diagram, the first input switch is 0. The second, generally we have used a normally open switch here. Okay, we have used a normally open switch. So when the first input is 0, second input is 0, means they will remain in their state, mean the normally open state. So no power will go to the output and there will be 0 output. Okay, so Y will be 0 in that case. Similarly in the second case, when A is 0 and B is 1. So here you can say the I0, since it is a normally open switch, when you will give 1 to the normally open switch, the second switch, it will change its state to the normally closed state. But here also the power will not flow throughout the rung, and output will the output switch will not get output will not get any power, and here in this case also the output will be 0. In the third case, when we are giving high input to the first switch and the 0 input to the second switch. So here you can say that when we are giving high input to the first switch, it will become normally closed. Okay, as I have said earlier, when you will give 1 input or high input, the switch will change its state. Since we are using the normally open switch, when you will give 1, it will change its state to the normally closed state. Okay, but the second input is 0, so it will remain in its normally open state. So the output in this case also will be 0. But in the fourth case, in which we are giving high input to both A and B, so both switch will change its state from normal open to the normal closed. So since now here the power will flow from the left rail to the right rail, and the output will get energized, so the output will be high and you will get a high output in that case. So here in this figure we have covered all the 4 cases of the AND gate. It will only get high, output will be only high when both the inputs will be high, and output will be 0 if in rest of all the condition for the 0 0, 0 1 and 1 0. Next, the OR function. The OR gate in the OR gate you will get the 0 only if both the conditions are 0. Okay, and you will get high or the 1 if any of the input is high or 1. Okay, it can be represented in the ladder diagram by the parallel connecting the switches. Here you can see in the diagram we have connected the two switches A and B in the parallel form, in the parallel connection with the output Y. Now in the next figure you can clearly see the four cases of the OR gate. Okay, in the first case, when both the inputs are 0, which means the input switch will remain in its state. Okay, it will remain in its open state. So both the switches are open, so the output will be 0. In the second case, when A is 0, B is 1, means first switch is getting 0 and the second switch is getting 1, which means the second switch will change its state from normally open to the normally closed state, and through this path of the second switch we will get the high output. Okay, so in that case the output will be high. In the third case, when first switch is getting 1 and second switch is at 0, the first switch, the A switch, will change its state from normally open to normally closed. Okay, and the second switch B will remain in its state since it is a 0 state. Okay, so in this case the output 1 will provide the power and the output will get a power. Okay, so in this case, in 1 0 you will get a high output. In the next case, when both the inputs are high or 1, means both the switch will change its state from normally open to the normally closed, and you will get a high output in this case. So in short, in all the three cases, since we have connected the switches in the parallel, normally open switches in the parallel connection, if any of the input is high, the output will be high, and if both the output will be 0, then only the output will be 0. Next, the NOT function. Here as I have seen, whatever output will provide, whatever input will be provided, the output will be just the inverse of it. Means if the input is 0, output will be 1. If input is 1, output will be 0. Here you can clearly see in the diagram, in the first case we have used the normally closed switch. Okay, so and if you are giving 0 state, it will remain in its normally closed state and you will get a high output. But in the second case, if you will give 1 or the high input to the switch, it will change its state. Since it is a type of normally closed switch, it will change its state to normally open and you will not get any power at the output and the output will 0. Okay, so this is the ladder diagram for the NOT function. So that's all for the today class, in which we have covered about the binary concept in detail, about the various AND gate, OR gate, NOT gate, universal gate, NAND gate, NOR gate, and the special gates XOR and XNOR. In the second, we have also covered the various PLC programming rules. Okay, and we have done the PLC programming for the basic gates, the AND gate, OR gate, and the NOT gate. And in the upcoming session, we will explore the PLC programming part in the detail, and we will do the PLC programming for the special gates, AND gate, NOR gate, XOR gate, and XNOR gate, and we will also use this PLC logic to program the industrial processes. Thank you. That's all for today. Happy learning.